All right, so if you can hear me or see me on the stream, then type yes in the chat so I know.
I couldn't see you.
Well, I'm not sitting in front of it anymore.
Oh, okay, no, I can see you. Okay. I can see you now. But if you stand in front of it, I can't see you. Yeah, so somehow that thing is writing, that thing is pointed this way. So now I can't see you, but when you're standing in front of the mic, I could see you.
You can see me here.
See even further.
Can you see the mic?
No, even this way.
Let me go see. Yeah, that's okay. I'm just mainly wondering if the sound is working. Okay, so yeah, people can.
Okay.
Okay, so I guess we'll get started. I can't actually hear the sound in here, but I have the chat open on my phone, so I'll see if you type something. So if something happens with the sound or the video screws up, let me know so I can stop talking and try and fix it. And so I also discovered that I uploaded the wrong YouTube or the wrong review video because I made that 2-hour review video and uploaded it, and I uploaded the wrong version, so it goes black after about half an hour. So right after this review, I'll upload the correct one. And the other thing is with this webinar, I'm not sure how the quality is going to be because I discovered a CPU problem with my computer and streaming. So anyway, hopefully this works, but if not, then we'll just have to cut it short and go to that YouTube video that I made, or the review video that I made earlier. But if this works out fine, then this video will be uploaded to YouTube basically right after the review. So I'll send out the link for that and also upload the correct review video. And so Dr. Deb is here, so if you have a specific question for him, then you can type that in the chat, and he has the chat open too. You have the chat, right? Just a second.
I need to open the chat. Say enter something.
Is it right under the video? Oh, so you can see it.
Okay.
So if they type a question, you'll see it. So yeah, if you have a specific question for him, then he has the chat open too. So for this review, the review I uploaded, it was really long, and so this one's going to be about an hour, and so I'm planning on cutting out some of the stuff I put in the other one, and so I'll just go through this and see how much stuff I can get through before we run out of time. So anyway, I have this sheet that he gave us, the competencies and problem types. And so I just wanted to kind of go through this. And so on the first thing he says to be familiar with is the conversion and mole balances. And this is chapter 1 and chapter 2 stuff. So chapter 1 was where you derived the mole balances for the flow rates. And then chapter 2 was where you put the mole balances in terms of conversion. And so I recommend looking at the summary in chapter 1 and chapter 2 at those equations. And when I took this class, I actually made a sheet where I went through and summarized those equations together because I felt like it was really helpful to see them all on the same page. And so it's just less confusing because there's a million equations. And then chapter 3 was the stoichiometry. And so as far as chapter 3, and the next section, the reaction rates and rate constants. So you need to be pretty familiar with deriving rate laws. And I did a bunch of videos on rate laws. So if you're having trouble deriving, say, the reversible rate law or the net rate law, then definitely go in and review that. And so and then also remember that the rates are highly dependent, or the rate constant is highly dependent on temperature. And then as far as the stoichiometry, make sure that you know how to set up the stoichiometric tables, sort of like the practice problems I did in class a few weeks ago. And then in chapter 4, so chapter 4 was kind of a summary of everything. So it was where you started combining everything. So chapter 1 and chapter 2 were the mole balances, and then chapter 3 was the rate laws and stoichiometry. And chapter 4 didn't really have anything new. It was just taking all of that and combining it. And so if you're feeling pretty confident with that stuff, it should be, so if you're feeling pretty confident with the stuff in chapter 1, 2, and 3, then going on to the further stuff, it's really just combining those equations and solving them. And even when you start getting into some of the other stuff, like adding in the pressure drop and looking at reactors that aren't isothermal, so I just highly recommend being really comfortable with the stuff in chapters 1, 2, and 3. And so for chapter 4, he says, mole balances and integrated rate expressions. And so it's basically just taking your mole balances that you did in chapter 1 and chapter 2 and combining that with the reaction rates and the stoichiometry from chapter 3, and then solving your problems. And he says to be familiar with the integrated rate expressions, but you don't need to memorize these, and you really shouldn't be trying to memorize these. If you go through, they should be pretty easy to derive. So, and then let's see, so then equilibrium considerations. So let's see, so he has writing rate equations for equilibrium reactions in terms of the forward rate constant and equilibrium constant. So definitely make sure you know how to derive the rate of reaction for a reversible reaction. And I did a video on that specific topic. So, and if the sound or anything happens, then definitely let me know. And so also you can find the equilibrium conversion by setting the rate to 0, and that makes sense because if you're at equilibrium, then your net rate will be 0. So just remember that. And then we also talked about multiple reactions, and that was in chapter 2 and chapter 4. And so he has be familiar with the knowledge, so it says knowledge about how staging reactors affects conversion, performing both graphical and equation-based calculations, equations for CSTRs in series, equations for incremental conversions for CSTR and PFR. And then I had an example problem where I'm going to go through a problem with multiple, or with several with reactors in series. And so in the review video that I did, the one that I need to re-upload, I had an example in there with Lebensspiel plots and also this problem I'm going to do now. So I'm not going to do the Lebensspiel plot problem for this particular review just because of time. So I'll just do this one. So this is reactors in series, and I'm going to get a different marker. So this is a liquid phase reaction, and you have A plus B to C. Thanks. And it's elementary. Actually, this one works worse. Oh, this one's good. Okay, so it's elementary, isothermal, and it just says you have a flow system. So CA naught is equal to CV naught is equal to 2 moles per dm cubed. And what you have here, just because I'm kind of getting ahead of myself with writing this stuff down, so you have a CSTR, and it's in series with a PFR. So when you have reactors in series, so I'm going to write CSTR, PFR, you'll have, I usually number what the conversions are. So you have some X naught coming in here, some X here, I'm going to call that X1, and then the conversion coming out of this reactor. So in this case, this will be 0 because there's no conversion going into the CSTR. And so then when the stream exits the CSTR and goes into the PFR, some conversion has already occurred. And so the way you solve this problem is you calculate the conversion from this that's coming out of the CSTR, and then that will be the conversion going into the PFR. So, and just to give you the rest of the data for this problem, so you have 2 reactors available. So you have so your CSTR is 200 dm cubed, and your PFR is 800 dm cubed. And K is equal to 0.07 at 300 K, and E is equal to 20 kilcal per mole. So, and then the question is, what is the conversion of X2, so the conversion of this system of reactors, if the CSTR and PFR are operated at 300 K and connected in series? And then the second part of the problem is if they're connected in parallel. And so to start this problem, I want to start with the CSTR. So I'm going to do a mole balance on the CSTR. And so then I just go to, and I want to write the mole balance in terms of conversion because that's what I'm looking for. And so I go to the summary in chapter 2 and look for the CSTR equation. And so that is V is equal to FA naught X out minus X in over minus RA out. And so these equations, these that are written in terms of conversion, they're see, what am I trying to say? So they're written with the X out and X in, and so normally when we write this equation, we're assuming that X in is 0, but in that chapter they're written like this. So when you're dealing with these reactors in series and parallel, or basically multiple reactors, make sure that you write down the entire equation and you don't just write V is equal to FA naught X out over RA. So in this case, the X in is 0, but I'd like to just write down the whole equation just to make sure I get it right. So, and then for the rate, you have minus RA is equal to K CA CB, and we know that it's K CA CB because it told us it was elementary. And so then for the stoichiometry, and it's liquids, so we have CA is equal to CA naught 1 minus X, and I'm going to write X1. I'm going to actually change this to X1 too, because that's what I'm looking for. So, and then CB is equal to CA naught 1 minus X1. So I'm going to erase some stuff, and then the next part of this problem is to just combine these equations and solve them. We're solving for X. So combine. So we have V is equal to, and I'm going to write FA naught as CA naught V naught, so that's FA naught. And then we have x1, because remember the xn is 0, over k CA naught, and then I'm plugging in the rate law, so this is actually CA naught squared 1 minus x1 squared. And then this can cancel. So we have, and at this point, I just plugged in all the values because these were all given. So we know what the volume is. I'm pretty sure V naught was given for this problem. K was given at 300, which is the temperature we're looking at. And let's see. Oh yeah, so V naught was given because it says the volumetric flow rate for each stream is 5 dm cubed per minute. So then you know it would be 10 because you're combining the two streams. Sorry, I didn't write that down. So I'll just write down the numbers. So the volume was 200 dm cubed, and this is equal to 10 because we had a stream of A and B coming in, and each stream, so we had A plus B to C, and the volumetric flow rate of each stream was 5 dm cubed per minute. So in this case, we're combining these because it's all going into one reactor. So this is 10 dm cubed per minute. And then we're looking for x1. And K was 0.07. And CA naught was 2 moles per dm cubed. That was also given. So 1 minus x squared. So then I just plug this into my calculator and I solve for x. And I got that x1 was equal to 0.55. So then we know that this x1 is 0.55. And so now we just need to go through the mole balance for the PFR. So now we just need to go through the mole balance for the PFR, and we can calculate x2, which is what we were looking for, I think. Yeah. So PFR mole balance. And so then we go to that table at the end of chapter 2 where it has the mole balances written in terms of conversion, and we get V is equal to FA naught x1 to x2 dx over minus RA. And so then I'm just going to go ahead and plug in the rate law because the rate law for this will be the same as the one we just calculated, so for the CSTR. So, and then FA naught is CA naught V naught. And so then we have x1 to x2 dx over, and then I'm plugging in the rate, which was CA naught squared 1 minus x squared, and then the CA naught cancels. So this is equal to V naught over K CA naught, because I'm pulling the K CA naught out. And this is x1 to x2, 1 over 1 minus x squared. And then this integration is on that table in the appendix. So this is equal to V is equal to V naught over K CA naught 1 over 1 minus x2 minus 1 minus x1. And so then I just plugged everything in. So we know the volume because it was given. We know V naught, we know K and CA naught, and we know x1 because we just calculated it. So I just plugged everything in and put this in my calculator and solved for x2. And I got that x2 is equal to 0.93. So anyway, that is, so these multiple reactor problems, it's basically the same idea for all of them. So I mean, if these were in a different order, then you just go through the same process. So it just goes back to make sure you know how to do the mole balances and derive your rate law. And let's see. So the next topic is so volume change in reactions and reactors. So this is for gas phase reactions, and so you need an equation of state, and we've been assuming the ideal gas law. And the main thing with that is just make sure that you're using the correct gas constant. And so then know what epsilon is, or know how to calculate epsilon. And then combining mole balances, rate expression, stoichiometry to obtain one equation. So that should be basically what we've already been doing, only in this case you would be adding in the equations for pressure drops. So you would modify your rate law to account for the, this isn't the pressure drop yet. So this is just if there's a volume change. So yeah, just make sure that you know how to go through the stoichiometry and account for if there's a volume change. And let's see. So then different types of reactors, and so he has semi-batch, so writing mole balances for a semi-batch reactor using either conversion formulation or number of moles formulation, and says a few problems can be solved analytically. Please see semi-batch examples from midterm 2. And then a lot of times with these problems you need to use an ODE solver, but we wanted to, Dr. Deb was actually going to go through a semi-batch problem that, just for an example. So
okay, so for the semi-batch problem, you basically know that you start with one of the constituents in the reactor. So A is inside the reactor, let's say, and B is coming in. And let's say we take a simple reaction, A plus B going to, in general it can be a reversible reaction, so we can say A plus B going to C plus D. So in this regard, one of the most important things you start with is the initial rate law, so or mole balance. So mole balance in terms of conversion for A would be minus RA multiplied by volume is going to be equal to Na naught times dx dt, where x is defined in terms of the conversion for A. So basically, to solve a problem in terms of conversion, you need to write the rate in terms of conversion, and then volume is changing as well. So volume in this case is going to be V naught. So initially you start with initial volume V naught, whatever volume you have in the system, plus the volumetric flow rate multiplied by time. So we have a changing volume in the system. That's something that you should be aware of. And the rate law can change, but whatever the rate law is, it will be provided to you. So let's say in this case the rate law is elementary but reversible. So it's going to be K multiplied by CA CB minus CC CD divided by K E or Kc, the equilibrium constant. So let's for the time being, let's just call it K. So once you plug the rate law into the mole balance, you need to make sure that the concentrations, all of the concentrations, are available in terms of the conversion of the species for which you are writing the conversion. So in this case, what is Ca going to be? So Ca is going to be equal to, so you start with, so just by definition, the number of moles of A that are left behind are Na0 multiplied by 1 minus x divided by V0 plus Vt. So it's actually divided by volume, but the volume is changing, so V0 plus Vt. Cb is going to be equal to, so the conversion for B is also going to be minus Na0 x. So let's say you start with NB0 initially. So NB0 minus Na0 x, which is the amount of B that is converted, plus B is coming in also, so you need to account for that. You need to account for B that is coming in. So that could be FB0 multiplied by time divided by same volume that is changing, V0. So in this case, supposing you don't start with any B at all, there is no B, then this term goes to 0. If you don't have any B that is being converted, if this is some kind of a catalyst that is being added, then this term is also 0. And then FB0 in this case, FB0 is CB0 multiplied by metric flow rate. So basically it gives you all of the things that you need to know to go to the rate expression. Similarly, you have CC, which is in this particular case simply Na0 times x, so it's the amount of C that is formed in that reaction divided by V0 plus Vt, and then CD is the same thing, Na0 times x divided by V0 plus Vt. Now, depending on the type of rate law that you have and what is happening in the reaction, when you substitute all of these things into the equation, you might be able to find a integral that you will be able to integrate analytically. And most of the time, the way you would integrate this analytically would be you would take x on one side and t on the other side. So you would have the general form of this would be something of the order of dx, then it will be some function of x, some function of x dx, 0 to x. So you separate that out, and then you'll have a bunch of constants here. Let's constants, integral of 0 to t dt, or some function of t, f of t dt. So this is the way you would integrate, and if you need to do some integration of this kind, I'm going to give you an integral table or something in the problem statement that will allow you to do the integration. So that's the way to solve a semi-batch problem that has a conversion formulation. Okay, we'll go over some of the other problems now.
Alright, so the next topic is different types of reactors, and then it has recycle reactor, which the recycle reactor isn't in the book, so you'll need to refer to the class notes or the author's webpage. And I also did a video on recycle reactors, so that might be a good review too. So it's basically basic definitions, integrated forms of equations with and without volume change. And so I have a problem I wanted to go through on that. So this is the recycle reactor. And so we have a first order reaction, A to B, A to B. And Ca naught is equal to 4 moles per liter. V is 200 liters. Your volumetric flow rate is 20 liters. And your recycle ratio, R, is 5. And X is equal to 0.6. So what we're actually doing with this problem is replacing the CSTR, so we're replacing the recycle reactor with the CSTR PFR combo. And so basically, you have a recycle reactor that you are getting this sort of conversion, and you're replacing that with the so I'm taking this to mean that you have a CSTR followed by a PFR. And it wants to know what volume of PFR is required to get the same X as the recycle reactor. So this problem is pretty much identical to the one I just did, and except in this case we know what X2 is, and so what we're trying to do is find the volume of this reactor, or the volume of the PFR that we need in order to get the same conversion. And so if you look at what we have as far as information, you'll notice that we don't have a rate constant. And so you can get the rate constant from the recycle reactor equation. And so I went through in the video the video that I made earlier for the review, I actually went through the mole balance, rate loss, stoichiometry, and I derived the recycle reactor first order integrated equation. But I'm not going to do that in this video because there's not going to be enough time. And so I'm just going to write it down. So you have tau k over r plus 1 is equal to the natural log of Ca naught plus r CAF over r plus 1 CAF. And so we should know everything we need to get k. We can calculate tau because we know that tau is v over v naught. We're given r. We know Ca naught, and we can calculate CAF because we know what the conversion is. So this is CAF is equal to Ca naught 1 minus x. And so you can go through and plug all these values in and get that k is equal to 0.1339 seconds minus 1. So then so from this point, this problem is basically identical to the one I just did. So you would calculate you would go through the mole balance, rate loss, stoichiometry for the CSTR and calculate x1. And then you go through so then you go through the same thing, like so you write a mole balance for your PFR, and it should be the same rate law that you use for the CSTR, and then your stoichiometry, and then you just solve your equation for B. So I'm not going to go through that because it really is pretty much the same thing as the problem I already did, but that's the process. So then the next topic is pressure drop in reactors. And so this is where I kind of got ahead of myself before. So with the pressure drop, you're still basically solving the exact same equations. The only difference is you need to account for the pressure drop in your stoichiometry, and then you also write and for your pressure drop. And so normally you would end up two coupled ODEs that you need to solve together, but in order to get an analytic, you can get an analytic solution if you basically assume that there's no volume change. So if you say that epsilon is equal to 0, then you can get an analytic solution. And so just keep that in mind. And if you make that assumption, make sure that you write down that you're making that assumption. And so then the next topic is data analysis. And so I wrote down to look at table 5-1 for this. So this is on page 254. Let's see. So, and I have the elements of chemical reaction engineering. And I know that this table is also in Essentials of Chemical Reaction Engineering, but I'm not sure which page it's on. But it's in this book is table 5-1, and it's called Steps in Analyzing Rate Data. And I feel like this table is pretty helpful in summarizing most of the stuff in this chapter. And so it just kind of steps you through how you solve for your rate order and rate constant if you have some data. And so I'm not going to really go through that table because I talked about it in the exam review I posted. But I wanted to do an example problem on data analysis, so I'm going to do that. All right, so data analysis. So I'm gonna. So this is a. So we have this reaction where we've run it multiple times in the lab and varied tau, and then measured Ca for the various taus. So let's just say we have run 1, 2, 3, and 4, and tau is. So we have tau, and we measured Ca for the various taus. So when tau was 1, Ca was 3.2. 15, Ca was 0.72. When tau was 3, Ca was 0.6. And when tau was 100, it was 0.21. And so we have this data. We know that this is a liquid reaction. It's irreversible. It's A to B, and it's in a CSTR. And we want to determine the reaction order and rate constants. So determine reaction order, alpha, and rate constant, K. So then you can go look at this table, and it says the first thing you want to do is postulate a rate law. So I'm going to say that the rate law looks like this. So minus RA is equal to K Ca alpha. Because I don't know what the reaction order is. And then the next step is select a reactor type and corresponding mole balance. So we know that this is a CSTR, so I'm going to write down the mole balance for a CSTR. So V is equal to FA naught minus FA over minus RA. But then my data is in terms of Ca and tau. So I want to put this equation in terms of Ca and tau. So we know that FA naught is equal to Ca naught V naught. So basically we can pull that out, and then we have Ca naught minus Ca over minus Ra. And then if we divide this V naught over, then we have tau is equal to Ca naught minus Ca over minus Ra. So then we can plug our assumed rate law in. So we have CA naught minus CA over K CA alpha. And so now I want to get this equation into a form that I can take the natural log and it'll look like a straight line. So what I'm going to do is multiply this K CA alpha over here and divide the CA naught minus CA by tau. So if I do that, I have CA naught minus CA over tau is equal to K CA alpha. And I'm just going to erase some stuff real quick. So then going back to this table, the next step is to take the natural log. So I'm going to do that. So if I take the natural log of this, I get ln of CA naught minus CA over tau is equal to the natural log of K plus alpha natural log of CA. And so then if you look at this, this should be y is equal to b, so mx plus b. So then alpha is the slope, and this natural log of the rate constant is b, or your y-intercept. So what you want to do is plot the natural log of CA naught minus CA over tau versus the natural log of CA. And so what I did was I just added to that table, which I already erased, but I just added a line and I calculated these, and I added another line and calculated this. So then I plotted these in my calculator and just did a linear regression, and I got that y is equal to 1.5x minus 0.286. So then I know that the order, alpha, is equal to 1.5, and this 0.286 is equal to the natural log of k. So then you can just solve for k, and you get that k is equal to 0.75. So these data analysis problems, it's kind of a big topic, and I don't want to, I can't talk about every detail of it, but I think if you review that table and review maybe the problems we had in the homework and the video I did on it, I think that would be a pretty good review of that topic. So the next thing is multiple reactions. And I marked table 6-1, which is on page 327. And so this table is called, I'll just try and show it. I don't know if you can see it, but you can look it up in your book. So this is called mole balances for multiple reactions. And I just felt like it was kind of helpful because it has the multiple reaction mole balances for the different types of reactors we've been learning about. And then on the next page is figure 6-5 is an algorithm for if you have multiple reactions. And so the big thing with multiple reactions is you need to write a mole balance for each reactant, whereas when we were doing the conversion, you just wrote it for one of the reactants. But for multiple reactions, you write your mole balances in terms of the molar flow rate, and you write it for each species. And the other thing is make sure you know how to write composite rate laws, so net rate laws. I feel like that's a really important thing to know how to do, and if you are proficient with that, you should also be doing the catalytic stuff where you need to write a net rate law for if you have sorption, surface reaction, and desorption. It should be pretty easy to come up with those rates also. So just make sure you are feeling pretty comfortable with that. And Let's see. So I wanted to do an example problem with multiple reactions. So I'm checking my chat real quick. Okay. So this is for a series reaction. So you have A to B to C, and this one's first order, and this one's second order. This is in a CSTR. So what you want to do is determine concentration of intermediate product B if tau is equal to 5 minutes. And then it gives K1 is 0.2 and K2 is 4 and Ca naught is equal to 1 mole per liter. And the units on these, this is minutes minus 1 and this is liters per mole minute. So the way you want to approach this, first we want to do a mole balance on A. So, or on this first reaction. So mole balance on first. And this is a CSTR, so this will be V is equal to FA naught minus FA over minus RA. And then if I pull so if I say, because I know that this is equal to Ca naught B naught, so I can just say V naught Ca naught minus Ca over minus RA. And then I could put this in terms of tau because it's giving us information in terms of tau. So we want to get our mole balance in terms of that. So tau is equal to Ca naught minus Ca over minus Ra. So then we want to do the rate law, and the rate for this is just K1 because it said it's first order. So then we can combine these, and we have tau is equal to C minus Ca over K1 Ca. And then if we solve this for Ca, we get that Ca, and it'll become apparent in a minute why we want Ca. So Ca is equal to Ca naught over K tau plus 1. So I'm going to erase some stuff real quick. So the next part of this problem is to do a mole balance on B. And so in order to do that, we need to, where did I have that? So I'll just write down so it's a CSTR mole balance. So I'll write that. And we have tau is equal to Cb naught minus Cb over minus Rb. And then, so where this problem really starts to change is with the rate law, because you need to do a net rate law, because really what you have here, if you were to rewrite this, you have, for your first reaction, you have A to B, and then for your second reaction, you have B to C. So you need to, this is basically you have a mole, B is in 2 reactions, so you need to account for that in your rate law. So minus RB is equal to RB1 plus RB2. And I don't think there's time to go through the details of deriving this, but I did a video specifically on this, so you might want to look at that if you're confused about how to get this, or look at the class notes or in the book. So, but this is equal to minus K1CA plus K2CB squared. Because remember, this one is second order. So then we can combine these equations, and so really I'm just going to plug that into there. So then I have tau is equal to CB naught minus CB over K1CA minus K2CB squared. And so then we already solved for CA, so we can just plug that in. And we're looking for CB. So you could either solve this equation for CB, or what I did was I calculated CA and put in a value, and then I put in a value for tau, CB naught, K1 and K2, and then I just solved for CB on my calculator, and I got that it was 0.135 moles per liter.
So some of the equations on this might be provided already, so in the handout, so they can look at that.
Which equations?
Series reactions, like the intermediate concentration.
So like this one?
Yeah, an optimum concentration of those two.
Okay.
For simple reactions, A going to B minus.
Do you want to just come tell them?
You just watch the handout for series reactions, just tell them that.
Okay, so Dr. Deff says that there's going to be a handout for series reactions, and so you would have,
You know some equations that take
So-
it directly.
so you'll have some equations already. So the next topic is heat effects, and so this is where you started looking at reactors that the temperature was changing in the reactor, or if it had a heating or cooling jacket. And so I think so I marked table 8-1, and that's something to definitely look at. And that's on page 476. So that's this table. I don't know if you can see that, but it's energy balances of common reactors. So this is a table that kind of summarizes all of the energy balances that are derived in this chapter. And so first one's adiabatic, and then CSTR with heat exchange, PBR, PFR with heat exchange, and then in terms of conversion, molar flow rates, semi-batch, and multiple reactions. And so the main thing to keep in mind is if you do pull an equation off this table, just make sure that it's not making an assumption that doesn't apply. So for instance, for this first one, the adiabatic assumes that the work is 0 and that delta C sub P is 0. So if that's true for you, then then you can use that, but just make sure that that's the case before using it. Because if it's not true, then you need to use a different equation that's not making that assumption. But I recommend being familiar with those equations and when to use them. And then also just the takeaways are for exothermic reaction, the equilibrium conversion decreases with temperature. And for an endothermic reaction, the equilibrium conversion increases with temperature. And let's see, I had some example problems on this, but I might just do one of them. Yeah, so I'm going to do a heat effects example problem. So heat effects. So this is in it's an elementary second order adiabatic reaction, and it's in a CSTR. So elementary second order adiabatic, and it's in a CSTR. And your reaction is A plus B to C plus D. Ca naught is equal to Cb naught is equal to 2.4 moles per liter. T naught is equal to 300 K. And your volumetric flow rate is 15 liters per minute. CPA is equal to 20. CPB is equal to 15. CPC is 15. CPD is 20. And I'm not going to write down the units just to save on time, but just looking at these right away, you know that delta C sub P is equal to 0. And let's see, the reactor volume, so it's asking, what is the reactor volume if X is equal to 0.75? So volume is question mark. And then it gives you your heat of reaction and K at 300 and E. So basically we have this adiabatic CSTR and we want to calculate the volume. So the first thing we want to do is a mole balance. So V is equal to FA naught X over minus RA. The rate law, it says it's elementary and it's second order, so the rate is equal to K CACB. For the stoichiometry, CA is equal to CA naught 1 minus X, and CB is equal to CA naught 1 minus X. And then we need to do an energy balance. So that's basically the added step for these problems, is you're basically doing all the same steps, but then you're adding in your energy balance because your temperature is changing. And so we can go look at this table in table 8-1, and we have an adiabatic CSTR. We know that delta C sub P is 0, and it's not saying anything about the work, so I'm assuming that's 0 too. So we can just pull the equation straight off that table, and so the one we want is T, it's the first one, so T is equal to T naught plus X, the heat of reaction over the sum of theta I CPI. So I'm going to erase some stuff real quick. So then we want to calculate what the temperature is, and the reason why we want to do that is because we need to know what temperature the reactor is operating at, so we can calculate K, because we know K at some temperature, we know K at 300, but it's not operating at 300, so we need to figure out what it's operating at so we can solve for K, and then we can just combine the mole balance rate law and stoichiometry and solve for the volume. So solving for T, we have that T is equal to T naught plus X, the heat of reaction. And then looking at this, we have theta A CPA plus theta B CPB. And technically it's true that you also have plus theta C CPC plus theta D CPD, but if you calculate theta C and theta D, they're 0. So then those terms would be 0. And in this case, theta A and theta B are equal to 1. So this is what we have here, only these are equal to 1, so let's take them off. And so then we have everything else. We know T naught, we know the heat of reaction, we know CPA, CPB, and we know X. So T is equal to 450 K. So then we solve for K at 450, and I'm not going to go through the details of that, but K is equal to 0.3694 liters per mole per minute at 450 K. and then we solve for V. So V is equal to CA naught V naught X over K CA naught squared 1 minus X squared. These cancel. And then we're given everything else, so we can just plug everything in with the correct K that we just calculated. And we get that this is equal to 203 liters. And then I did, so in the video that I posted earlier that I'm going to repost, I went over another heat balance or another heat problem, and so the second problem I did was graphically, and so I'm not going to go over that right now because we're running out of time, but definitely make sure that you know how to calculate and plot the X mole balance and your conversion mole balance and your conversion energy balance, and make sure you know how to figure out steady states based on those plots. And so then let's see, so then we started getting into reactors that weren't necessarily ideal. And so, for instance, we looked at diffusion and a catalyst. So if you have a catalyst, there's going to be, so you have what would happen ideally, and then you have what actually happens. And so we looked at this thing called the effectiveness factor. And I went through an example problem on that in the video, which I'm also going to skip here just because of time. So make sure you know how to apply the effectiveness factor to your problems. And so let's see. So I think that is about it. So, and then the last topic was residence time distributions, which that won't be on the exam. So you don't need to worry about that. And so that's pretty much it. If there are any last minute questions, then try and post it in the next minute or two. So is there anything you want to tell them about the exam?
No.
Okay.
I already posted something on campus, so they should have.
Okay. So assuming everything for this video actually streamed and recorded okay, then I'll be posting it. And so, let's see. I don't see any more questions, so I guess we're going to wrap it up, and good luck tomorrow.